Namaste. Today we're diving deep into the chapter on magnetic effects of electric current. I'm really keen to understand how these invisible forces actually work and, their impact.
Excellent choice. And namaste to you, too. This deep dive is absolutely fundamental. Seriously, not just for scoring high in your Class 10 board exams where it's, well, pretty much a guaranteed topic. But it also lays the real groundwork for advanced physics concepts you'll hit in Class 11 and 12.
Okay, so it connects further up.
Absolutely. These principles are crucial for the big competitive exams like JE and NEET, and even the general science section of major government service exams like UPSC, SSC, and state PSCs too.
Wow, so it's quite widely applicable then.
It really is. And the effects we're about to explore, they're literally everywhere around us. Think about the simple electric doorbell at home. Or, on the other end of the scale, those incredibly powerful, life-saving MRI machines in hospitals.
Right, from doorbells to MRIs, that's quite a range.
Exactly. So it's not just abstract theory, it's deeply practical stuff. Our mission today, basically, is to systematically unpack how electricity creates magnetism, how these magnetic fields behave, understand the forces involved when a current interacts with a field, and then we'll wrap up by looking at their practical applications. That includes some crucial safety measures within our own homes, our electrical circuits.
Okay, sounds like a plan. Where do we start?
Let's take this step by step and really try to grasp each concept thoroughly. All right, let's unpack this. In our last deep dive on electricity, remember we spent quite a bit of time on the heating effects of electric current.
Yeah, like how nichrome wire heats up in a toaster or an electric heater.
Precisely. How an electric geyser heats water, or an electric iron presses clothes. Now we're going to explore another equally fascinating and incredibly important effect of electric current. Its magnetic effect.
Okay.
This core idea that an electric current-carrying wire behaves like a magnet might seem, well, sort of straightforward today, but it wasn't always understood. Actually, its discovery was quite groundbreaking.
Really? How did they figure it out?
Well, to truly appreciate this fundamental connection, let's maybe think about activity 12.1 from the textbook. It beautifully replicates the historic Oersted's experiment.
Oersted, right.
Imagine taking a thick copper wire, connecting it into a simple electric circuit. You place this wire vertically, say perpendicular to a table surface, and then very close by, you position a small magnetic compass.
Okay, got the setup in mind. Wire, circuit, compass nearby.
Now the crucial step, when you complete the circuit, you press the key and allow current to actually flow through that wire. What happens?
The compass needle moves.
Exactly. The compass needle immediately deflects from its usual north-south alignment. This seemingly simple observation is, well, profoundly significant.
Why is it so significant?
Because it means the electric current flowing through the copper wire has produced a magnetic field around it. A field strong enough to affect the tiny magnet of the compass needle. This experiment, simple as it sounds, revealed the intrinsic link between electricity and magnetism. It showed they are, in fact, two sides of the same coin. Electromagnetism.
Wow. Just from a twitching needle?
Yep. And here's where the history gets really interesting. This pivotal, almost accidental discovery was made by the Danish physicist Hans Christian Oersted back in 1820.
Accidental.
Pretty much. He was actually giving a lecture demonstration, and quite unexpectedly, he noticed a nearby compass needle deflected whenever he switched on an electric current in a metallic wire he was using. It wasn't like he set out to find this specific effect. It was, pure scientific serendipity.
So he just noticed it by chance during a class.
Exactly. But Oersted, having a keen scientific eye, didn't just dismiss it as a weird fluke. He pursued this seemingly small observation. His subsequent research completely revolutionized our understanding of electromagnetism.
So he followed up on it properly.
He did. And his work didn't just stay in textbooks. It literally paved the way for countless technologies we now completely take for granted. Things like radio, television, even the fiber optics that power our internet these days.
No way. All from that compass needle moving.
It kick-started the whole field. In fact, in his honor, the unit of magnetic field strength in the old CGS system, that's the centimeter gram second system, is named the Oersted. So yeah, a tiny deflection led to a global technological revolution.
That's truly fascinating. So, okay, electricity can definitely produce magnetism, but this makes me think. Is it a one-way street? Can magnetism, do the reverse? Can it produce electricity? Like if I just wiggle a magnet near a wire, could I get a current?
That's a remarkably insightful question, and it shows you're thinking like a true physicist. You're pointing directly towards the concept of electromagnetic induction.
Electromagnetic induction, okay.
Which is something we'll definitely explore in detail in future deep dives. And yes, the short answer is the reverse is absolutely possible. A changing magnetic field, or even just the relative motion between a conductor and a magnetic field, can indeed induce an electric current in the conductor.
Wow, so moving magnets can make electricity.
They can. This phenomenon is fundamental to how electric generators work, the massive ones in power plants that, well, power our entire modern world. But to fully grasp that really exciting possibility, we first need to solidify our understanding of magnetic fields themselves. How they're represented, what are their fundamental properties, and how they interact.
Right, first things first. Let's get the basics of magnetic fields down.
Exactly. So let's dive into the core concept of magnetic fields and how we represent them using these things called magnetic field lines. We're all familiar, I think, with how a compass needle behaves when you bring it near a bar magnet.
Yeah, it points towards it or away, depending on the pole.
Right, it immediately gets deflected and aligns itself in a certain way. Remember, a compass needle itself is actually just a very tiny, lightweight bar magnet that's free to rotate. It has its own north-seeking pole and a south-seeking pole.
Okay, it's a tiny magnet.
And just like, well, not people, but like fundamental forces, magnets have their rules, or fundamental interaction rules. Like poles repel each other. North repels north, south repels south.
Right, opposites attract, likes repel.
Exactly.
Yeah.
Conversely, unlike poles attract each other, so a north pole will strongly pull towards a south pole. This fundamental interaction governs how magnets exert forces on each other and on other magnetic materials.
Okay, that's the basic force rule. How do we see the field?
Good question. To really visualize this invisible force field, let's think about activity 12.2, the one using iron filings. It's a classic.
Yeah, I remember seeing pictures of that.
Imagine taking a simple bar magnet and placing it right in the center of a white sheet of paper. Now, you take some fine iron filings, you can get them easily, and sprinkle them uniformly all around the bar magnet.
Just sprinkle them randomly.
Yeah, just scatter them around. Once sprinkled, gently tap the drawing board or the paper a few times. And what do you observe?
The filings make a pattern, right? They line up in curves.
Precisely. You'll see the iron filings immediately arrange themselves in a distinct, quite beautiful pattern around the magnet. They form these curves that seem to emerge from one pole and loop around to enter the other. This pattern vividly demonstrates the presence of a magnetic field.
So the field is that whole region of influence.
Yes, it's the region surrounding any magnet where its force or influence could be detected. And the lines formed by the iron filings are a direct visual representation of these magnetic field lines. They literally show you the paths along which a hypothetical free north pole would tend to move if you placed it there.
Okay, iron filings give a good picture. Is there a more precise way?
Absolutely. We can draw these magnetic field lines even more precisely, as shown in activity 12.3, using a compass.
Using the compass itself to trace the lines.
Exactly. Again, place your bar magnet on a white sheet of paper. Fix onto a drawing board. First step, carefully mark the exact boundary of the magnet on the paper. Now, take your small magnetic compass. Start by placing it near the north pole of the bar magnet.
Okay, near the North Pole.
Observe how it behaves. The south pole of the compass needle will naturally point towards the magnet's strong north pole, because unlike poles attract, the compass's north pole will point away. Now, mark the exact position of both ends, the north and south poles of a compass needle with tiny dots on the paper.
Got it. Mark both ends.
Now, here's the clever part. You move the compass to a new position, such that its south pole now occupies the position previously held by its north pole.
So you step along the direction the North Pole was pointing.
Precisely. You continue this step-by-step process, marking the new position of the compass's north pole each time. You keep doing this dot by dot, tracing a path all the way until you reach the south pole of the bar magnet.
Okay, following the needle's direction.
Once you've done this, joining these marked points with a smooth, continuous curve gives you one complete magnetic field line.
Just one line.
One line, yes. But then you repeat this entire procedure, starting from different points near the North Pole. This allows you to draw many such lines around the magnet. When you're done, you'll see a complete pattern, much like the one formed by the iron filings, but more precisely drawn. It reveals the entire magnetic field landscape around the magnet. This activity really helps you appreciate that invisible structure.
That's a very clear way to visualize these lines step by step. So now we have these lines. How do we precisely define their direction and strength? And are there any specific rules about how these magnetic field lines behave or interact? This seems like it would be really important for exams, both boards and competitive ones.
You're absolutely right. That's a sharp question, and it's definitely a favorite for examiners. You'll find these properties popping up frequently, so really understanding them is key. Let's break down the crucial properties of magnetic field lines.
Okay, let's list them out.
First, and this is fundamental, a magnetic field is a vector quantity. Remember what that means?
It has both magnitude, like strength, and direction.
Exactly. It possesses both direction and magnitude. Now, by convention, the direction of the magnetic field at any given point in space is defined as the direction a hypothetical, isolated North Pole would move if it were placed freely at that point. Imagine a tiny, free North Pole. Its path would essentially trace out the field line. The tangent to the field line at any point gives the direction of the field at that point.
Okay, direction follows a hypothetical North Pole. What's next?
Second, regarding their origin and termination, or where they start and end. Conventionally, magnetic field lines are always shown emerging from the North Pole of the magnet, spreading out into the surrounding region, and then looping around and merging into the South Pole outside the magnet. We'll always see arrows on these lines indicating this outward flow from north and inward flow towards south.
Right, north to south outside.
But, and here's a detail often missed, but one that's very important for a complete understanding and often tested. Inside the magnet itself, the direction of the field lines is from the South Pole back to the North Pole.
Oh, so they go through the magnet, south to north inside.
Exactly. Think about this carefully. If they emerge from north and enter south outside, and then go from south to north inside, what does that tell us about the lines themselves?
They don't really start or end. They're like loops.
Precisely. It means magnetic field lines are, in fact, closed curves. They form continuous loops, never beginning or ending. You can visualize this like a continuous rubber band stretching from the North Pole, looping around outside, entering the South Pole, and then completing its circuit by stretching through the magnet's interior back to the North Pole. This closed loop property is fundamental and frequently tested.
Okay, closed loops. That's important. Property 3.
Third, the relative strength of the magnetic field is indicated by the degree of closeness, or the density of the field lines. Where the lines are crowded together, where they are closer to each other, the magnetic field is stronger.
Like near the poles.
Exactly. This means that if you were to place another magnet's pole in that region, the force acting on it would be greater. Think of it like contour lines on a topographical map. Closer contour lines mean a steeper incline, or in this case, a stronger field. Conversely, where the lines are farther apart, like midway between the poles, but further out, the field is weaker. This perfectly explains why the force of a magnet feels strongest right at its poles, because that's where the field lines are most concentrated.
Makes sense. More lines packed together means stronger field. What else?
And finally, this is a vital property that comes up in almost every exam. No two magnetic field lines ever intersect each other. They can get very close, but they never cross.
Why not? What would happen if they did cross?
Think about it. If they did intersect at some point, what would that imply? Remember, the direction of the field at any point is given by the tangent to the field line. So if two lines crossed, there would be two possible tangents at the point of intersection. This would mean that at that single point, a compass needle, which, remember, aligns itself with the magnetic field direction, would have to point in two different directions simultaneously.
Oh, right. That's impossible. A compass can only point one way at one spot.
Exactly. It's physically impossible for a single compass needle. It can only point in one definite direction at any given point in space. So the non-intersecting nature of field lines is a fundamental consequence of the field having a unique direction at every point. Mastering these properties, vector nature, north to south outside, south to north inside, closed loops, density indicates strength, and non-intersection is absolutely key.
Okay, got those properties.
Yeah.
Very clear.
No.
So we know about fields from magnets. What about the fields from currents, like Oersted saw?
Excellent transition. So we've mapped out the invisible landscape around permanent magnets. But remember Oersted's initial discovery. Electric currents also create these fields. This immediately begs the question, what do those fields look like? Are they just like miniature bar magnet fields, or is there a completely new, unique pattern that emerges from a flowing current?
Yeah, are they loops too, or something different?
That's exactly what we need to explore now. Let's start with the simplest case. The magnetic field around a long, straight, current-carrying conductor.
Okay, a straight wire with current.
If we refine Oersted's original experiment, sort of like in Activity 12.4, we can learn more about the direction of this magnetic field. Imagine again a long, straight copper wire. This time, place it parallel to and directly over a small magnetic compass needle.
Wire over the compass.
First, let's make the current flow from north to south through the wire. What you'd observe is the north pole of the compass needle deflecting towards the east.
Okay, north to south current makes the needle point east.
Now, if you simply reverse the battery connections, so the current now flows from south to north through the same wire, what do you think happens?
It deflects the other way, towards the west.
Exactly. The compass needle's north pole will now deflect towards the west. This direct observation clearly demonstrates that reversing the direction of the electric current reverses the direction of the magnetic field it produces. The magnetic field direction is intrinsically tied to the current's direction.
Okay, direction depends on current direction. What about the field strength?
Good question. Two key relationships here, also hinted at by observing the compass deflection. First, if you increase the current flowing through the wire, maybe by adjusting a rheostat in the circuit, the compass needle's deflection also increases. It swings further.
More current, bigger deflection.
Right. This means the magnitude or strength of the magnetic field produced at a given point is directly proportional to the current passing through the wire. More current means a stronger magnetic field.
Okay, proportional to current. What about distance?
Second observation. If you move the compass farther away from the wire, while keeping the current the same, the deflection visibly decreases. The needle doesn't move as much.
Further away, less deflection.
Correct. This tells us that the magnetic field produced by a current-carrying conductor decreases as the distance from it increases. The field is strongest right near the wire and weakens progressively as you move away. These relationships, directly proportional to current, inversely related to distance, are vital for understanding the field and for numerical problems in competitive exams.
Got it. Stronger, closer, weaker, farther. Proportional to current. Now, what does the actual pattern look like? Is it straight lines?
The pattern. To visualize the pattern of these magnetic field lines around a straight current-carrying wire, we need to think about activity 12.5.
Okay, activity 12.5. What's the setup?
Imagine inserting a thick copper wire vertically through the center of a flat piece of rectangular cardboard. You need to fix the cardboard so it doesn't wobble, and the wire passes straight through it, perpendicular to the cardboard surface.
Like poking a wire through a horizontal sheet of paper.
Exactly. Then you connect the ends of this wire to a power source, probably a battery, maybe you include a rheostat to control the current, and a key to switch it on and off. Now, sprinkle some iron filings uniformly on the surface of the cardboard, all around the wire.
Okay, iron filings again.
Once you switch on the current, gently tap the cardboard a few times. What pattern do you think emerges this time?
If the field gets weaker further away, maybe circles.
You got it. You will observe the iron filings arranging themselves in a beautiful pattern of concentric circles centered on the copper wire. These concentric circles are the magnetic field lines for a straight, current-carrying conductor.
Concentric circles. Okay, that's different from a bar magnet.
Very different. And consistent with our earlier observation about strength and distance, these circles become larger and sparser, more spread out as you move away from the wire. This visually reflects the decreasing field strength with distance.
And the direction. How do we know if the circles go clockwise or counterclockwise?
Good point. You can find the direction by placing a small compass on one of these circles formed by the filings. Its north pole will point along the tangent to the circle, indicating the direction of the field line at that specific point. And crucially, if you reverse the direction of the current flowing through the wire, the direction indicated by the compass needle on these circular field lines will also reverse.
Okay, so compass tells the direction. But it's really interesting how the iron filings form those perfect concentric circles. Is there a simpler way, like a rule or a trick, to figure out the direction of these circles without needing a compass every single time? I'm thinking about exams needing to find the direction quickly seems important.
You've hit on a very practical point, and absolutely there is. This is where the right-hand thumb rule comes in. It's a fundamental principle in electromagnetism, super handy, and honestly indispensable for competitive exams where you need quick directional analysis.
Right-hand thumb rule. Okay, how does that work?
Here's how it works. Imagine you are holding the current-carrying straight conductor, that copper wire we just discussed, in your right hand. Grip it like you'd hold a screwdriver or a pole.
Okay, holding the wire in my right hand.
Now, orient your hand so that your thumb points precisely in the direction of the electric current flow through the wire. Let's say the current is flowing upwards, so point your thumb upwards.
Thumb points along the current. Got it.
Once your thumb is pointing in the direction of the current, look at how your fingers naturally wrap or curl around the conductor. The direction in which your fingers wrap around the conductor gives you the exact direction of the magnetic field lines, those concentric circles.
Ah, so if current is up, my fingers curl around counterclockwise if I look from above.
Exactly. It's incredibly intuitive once you try it. I strongly encourage everyone listening. Right now, try this gesture yourself to visualize it. Hold an imaginary pen or pencil, representing the wire, in your right hand. Point your thumb up for current direction and see how your fingers curl around it. That curl is the magnetic field direction.
Okay, that seems pretty straightforward. Thumb for current, fingers for field.
Precisely. This rule is also sometimes known as Maxwell's corkscrew rule. It's another helpful visualization. Think of driving a normal right-handed corkscrew into, say, a piece of wood. If the direction you're driving the corkscrew in represents the direction of the current, then the direction your hand rotates the corkscrew is the direction of the magnetic field.
Ah, like screwing something in. Clockwise rotation usually drives it forward.
Right. Both rules essentially convey the same fundamental relationship between current direction and field direction for a straight wire.
Okay, let's try applying it. You mentioned an example.
Yes, let's apply this with a classic example often seen in exams. Imagine a horizontal power line, like the ones you see outside, that carries electric current from the east direction towards the west direction.
Okay, current flows east to west.
The question is, what is the direction of the magnetic field at a point directly below this power line and also at a point directly above it?
Okay. Using the rule, I hold the wire in my right hand, thumb points west, direction of current.
Correct. Now, how do your fingers curl around the wire?
My fingers curl. Underneath the wire, they point towards the south, and above the wire, they point towards the north.
Perfect. Below the wire, your fingers point south. Above the wire, they point north. If you were looking at the wire from the east end, looking west, your fingers would be curling in a clockwise direction. If you looked from the west end, looking east, it would appear anti-clockwise. So below the wire, field is southwards. Above, it's northwards. Practice visualizing this with your hand. It's the best way to internalize the rule for quick application in problems.
Got it. That rule seems really useful. Now, what happens if the wire isn't straight? What if we bend that straight wire into a circular loop? How does the field pattern change then?
Good question. Let's move from straight wires to circular loops. The fundamental principle actually remains the same. Every tiny segment of that circular loop carrying current still creates its own little set of concentric magnetic field lines around it, just like a tiny piece of straight wire would.
So each bit of the loop makes its own circles.
Exactly. However, because it's a loop, these concentric circles generated by all the different segments start to interact and overlap. As we move away from any particular segment of the wire towards the center of the loop, these concentric circles get larger and larger. By the time we reach the exact center of the entire circular loop, the arcs of these very large circles from all segments will appear almost as straight lines, all passing through the center.
Okay, so near the wire it circles, but at the center it becomes straighter.
Yes, and here's the key part. If you meticulously apply the right-hand thumb rule to every small section of that circular wire, let's imagine the current is flowing clockwise around the loop. You'll find something interesting. All these individual sections contribute to the magnetic field lines pointing in the same direction within the loop, specifically at the center.
Ah, so they all add up in the middle.
Precisely. They reinforce each other at the center. This means the magnetic field at the center of a current-carrying circular loop is relatively strong and points uniformly in one direction, either straight into the plane of the loop or straight out of it, depending entirely on whether the current is clockwise or counterclockwise. This concentration of the field at the center is a key characteristic.
Okay, the field is strong and uniform at the center of the loop. What if we have more than one loop, like a coil?
Excellent point. This leads us directly to another important concept, often tested in multiple-choice questions, the effect of the number of turns. For a circular coil that has a number of turns, meaning it's not just one loop, but many loops wound tightly together, maybe like a flat spiral or stacked loops.
Like winding wire around a cylinder multiple times.
Yes, or just multiple loops in a plane. The magnetic field produced at its center is found to be n times as large as the field produced by just a single turn carrying the same current.
So 10 turns means 10 times the field.
Exactly, assuming the same current.
Yeah.
Why is this? It's simply because the current in each individual circular turn flows in the same direction, either all clockwise or all counterclockwise. Therefore, the magnetic fields produced by each turn simply add up constructively at the center, making the combined field much stronger. So the simple takeaway: more turns, stronger magnetic field at the center for the same current. Activity 12.6, by the way, allows you to visually observe this pattern using iron filings again if you pass a circular coil through cardboard.
That makes perfect sense. If increasing the number of turns makes the magnetic field stronger at the center, what if we take this idea further? What if we coil the wire many, many times in a very specific, elongated shape, like a spring, maybe? Could that create an even more useful or interesting magnetic field?
Excellent thought. You're leading right into the next crucial component. That specific shape you're describing is precisely what we call a solenoid. And yes, it creates a very useful and interesting magnetic field. Solenoids are extremely important components in countless electrical devices, from simple things like electric door locks and valves to complex industrial machinery and scientific instruments.
A solenoid? Okay, so what exactly defines it? Just a long coil?
Essentially, yes. A solenoid is basically a coil of many, many circular turns of insulated copper wire wrapped very closely together, specifically in the shape of a cylinder. Think of it exactly like a spring that you stretch out, or a coiled garden hose. It's long and cylindrical, made up of numerous loops packed tightly side by side.
Got it. A long cylindrical coil. What's special about its magnetic field?
What's fascinating about a current-carrying solenoid is its magnetic field pattern. When you pass current through the wire, the overall magnetic field pattern it produces around itself is remarkably similar to that of a classic bar magnet.
Really? It acts like a bar magnet.
It does. One end of the solenoid behaves like a magnetic north pole, where the field lines appear to emerge and loop outwards, and the other end behaves like a magnetic south pole, where the field lines loop back in and appear to merge. You can even determine which end is north and which is south, using a variation of the right-hand rule, often called the right-hand grip rule for solenoids.
So we can make a magnet just by coiling wire and passing current.
Precisely. But here's the most crucial property of a solenoid, and one that is highly important for both theoretical understanding and for solving problems, especially in competitive exams like JE and NEET. It's about the field inside the solenoid.
Okay, what about the field inside?
The field lines inside a long solenoid are almost perfectly parallel straight lines, running along the axis of the cylinder, and they're evenly spaced.
Parallel straight lines inside. What does that signify?
This signifies something very significant. It indicates that the magnetic field is essentially uniform at all points deep inside the solenoid, away from the ends. Uniform means it has the same strength and the same direction everywhere within that central region. This characteristic of producing a strong, controllable, uniform magnetic field inside is what makes solenoids so incredibly useful.
A uniform field inside, I can see how that might be useful. How is it applied?
Well, this strong, uniform magnetic field produced inside a solenoid has a powerful and incredibly common application. It can be used to magnetize a piece of magnetic material, most commonly soft iron, when that material is placed inside the coil.
So you put iron inside the coil, turn on the current.
And the iron becomes strongly magnetized. The magnet formed this way is called an electromagnet.
An electromagnet.
Right. These are not like your permanent bar magnets. They are temporary magnets. Their magnetism exists only as long as the current flows through the solenoid. Crucially, their strength can be precisely controlled simply by varying the current flowing through the solenoid's wire. Increase the current, the electromagnet gets stronger. Reduce or switch off the current, it weakens or loses its magnetism almost completely, especially if the core is soft iron.
So you can turn the magnetism on and off?
Exactly, and adjust its strength. This control is invaluable. Think of those powerful magnets used in scrapyards to lift and move heavy metal objects, like entire cars or large steel beams. Those are almost always large electromagnets. They can be switched on to attract and lift the metal, moved to the desired location, and then switched off to release it. This is a direct, practical outcome of understanding the magnetic effect of electric current in the solenoid.
Wow, okay. From simple rules to lifting cars, that's impressive. So we know current makes a field. What about the other way around? Does a field affect a current? You mentioned ampere earlier.
Yes, absolutely. Let's move on to that equally important concept. The force exerted on a current-carrying conductor when it's placed in an external magnetic field. We've clearly established that an electric current creates its own magnetic field. We also know from basic magnet interactions and the compass deflection that a magnetic field exerts a force on a magnet placed nearby.
Right.
Building on this, the brilliant French scientist André-Marie Ampère, way back in the early 19th century, made a profound suggestion based on logic and symmetry. He reasoned, If the current-carrying wire acts like a magnet, as Oersted showed, and exerts a force on a stationary magnet, like the compass, then by Newton's third law, the law of action and reaction, the stationary magnet must also exert an equal and opposite force back on the current-carrying conductor.
Ah, action-reaction. If the wire pushes the magnet must push the wire.
Exactly. It was a theoretical leap at the time, but it was later definitively proven by experiments. There is a force on a current-carrying wire placed in a magnetic field.
Can we see this force in action? Is there an experiment for that?
Yes, we can demonstrate this force and the resulting displacement quite clearly through activity 12.7. Let's try to set it up in our minds. Imagine a small, lightweight aluminum rod, maybe about 5 centimeters long, suspended horizontally from a stand using 2 flexible connecting wires so it can swing freely.
Okay, a hanging aluminum rod.
Now, place a strong horseshoe magnet around this aluminum rod. A horseshoe magnet provides a relatively uniform field between its poles. Position it in a very specific way, and ensure the rod lies between the north and south poles of the magnet. And crucially, let's arrange the magnet so its north pole is vertically below the rod and its south pole is vertically above the rod.
North below, south above, so the magnetic field between the poles is pointing upwards.
Exactly. This configuration creates a magnetic field that is directed vertically upwards, passing through the region where the aluminum rod is suspended. Now connect the ends of the aluminum rod, via the suspension wires, in series with a battery, a key, and maybe a rheostat to control the current.
Okay, rod in the upward field, ready to pass current through it. What happens when we switch it on?
Now, pass a current through the aluminum rod, let's say, for end B to end A, just picking directions. What do you observe the moment the current starts flowing?
Based on Ampere's idea, the rod should move.
It does. The rod is immediately displaced. It visibly moves. Perhaps it swings towards the left. This is tangible proof that a force is acting on the current-carrying rod due to the magnetic field.
Wow, it actually pushes the rod.
Yes. Now, let's try a variation. Reverse the direction of the current flow through the rod using the battery connections. So now current flows from A to B. What happens?
If reversing current reverses the field it creates, maybe it reverses the force too. Does it move right now?
Spot on. The rod will now displace towards the right. The direction of the force clearly reverses when the direction of the current reverses.
Okay, force depends on current direction. What about the field direction?
Let's test that too. What if we reverse the magnetic field direction? We can do this by simply flipping the horseshoe magnet over, so the north pole is now above the rod and the south pole is below. Now the magnetic field through the rod is pointing vertically downwards. If we pass the current in the original direction, B to A, what happens to the force?
If reversing current reverses the force, maybe reversing the field also reverses the force.
You got it. The direction of the force acting on the rod reverses again. If it moved left before with upward field, it will now move right with downward field, assuming the current direction is the same in both cases.
Okay, so the force direction depends on both the current direction and the magnetic field direction.
Precisely. These key observations from activity 12.7 lead to some vital conclusions, absolutely crucial for exams. Firstly, it clearly shows that a force is indeed exerted on a current-carrying conductor when it is placed in an external magnetic field. Secondly, and very importantly, the direction of this force depends simultaneously on both the direction of the electric current flowing through the conductor and the direction of the external magnetic field. Change either one, and the force direction changes.
And is the force always the same strength?
Good point. No. Thirdly, through various quantitative experiments, it has been shown that the magnitude of this force, how strong the push or pull is largest when the direction of the current is at right angles, that is, perfectly perpendicular 90 degrees to the direction of the magnetic field.
So maximum force when they're perpendicular. What if they're parallel?
If the current is flowing parallel or anti-parallel to the magnetic field, the force is actually zero. The conductor experiences no magnetic force in that case. The force is maximum at 90 degrees and decreases as the angle moves away from 90, becoming zero at 0 and 180 degrees. This dependence on the angle, specifically the sign of the angle, is something you'll delve into more deeply in Class 11-12 physics. But the key takeaway for now is maximum force occurs when current and field are perpendicular.
That's incredible. So this force makes conductors move. It seems like the direction of current and the magnetic field are both crucial in determining the direction of that movement. Is there another rule, a simple trick, maybe using hands again, to figure out which way the conductor will actually move? I'm imagining needing to figure this out quickly on an exam, and trying to deduce it from scratch every time seems slow and prone to error.
You've anticipated the next essential tool perfectly. There absolutely is a rule for this, and it's called Fleming's left-hand rule. This rule is not just vital for theoretical understanding, it's absolutely essential for comprehending the working principle of electric motors and for rapidly solving those directional problems you encounter in competitive exams. Get this rule wrong, and you get the motor direction wrong or the force direction wrong in a problem.
Fleming's left-hand rule this time. Okay, the other was right-hand thumb rule. How does the left-hand rule work?
Let's learn how to apply it. You need your left hand for this one. Stretch out the thumb, the forefinger, your first or index finger, and the middle finger, your second finger, of your left hand so that they're all mutually perpendicular to each other.
Mutually perpendicular, like the X, Y, and Z axes in math, all at 90 degrees to each other.
Exactly like that. Imagine them forming the three axes of the 3D coordinate system. It might feel a bit awkward at first, but get them nicely perpendicular. Thumb pointing up, forefinger pointing straight ahead, middle finger pointing off to the side, all at right angles.
Okay, got the awkward hand pose. Now what do the fingers represent?
Now let's assign their roles. This is the crucial part to memorize. Your forefinger, the first finger, points in the direction of the magnetic field. Remember, this is the external field, conventionally directed from the North Pole to the South Pole outside the magnet.
Forefinger field, okay.
Your middle finger, the second finger, points in the direction of the current flowing through the conductor.
Yeah.
This is the conventional current direction.
Middle finger, okay.
And then, quite simply, if you've aligned your forefinger with the field and your middle finger with the current, your thumb will automatically point in the direction of the motion or the force acting on the conductor. This is the direction in which the conductor will tend to move or experience a push.
The thumb, force motion. Okay, field, current, force motion. Using forefinger, middle finger, thumb of the left hand.
Precisely. I strongly encourage everyone listening to practice this gesture with your left hand right now while listening. Point your fingers according to field and current, and see where your thumb points for the force. It helps immensely with visualization and memory. And here's a common mnemonic that many students find helpful to remember the order. Think father, mother, child.
Father, mother, child. How does that relate?
F for father relates to F for force, represented by the thumb. M for mother relates to M for magnetic field, represented by the forefinger. And C for child relates to C for current, represented by the middle finger. So in order, thumb force, forefinger field, middle finger current, father, mother, child. It can help lock it in.
Father, force thumb, mother, field, forefinger, child, current, middle. Okay, that might stick. Can we try an example, like the ones in competitive exams?
Definitely. Let's tackle a classic competitive exam-style question to apply Fleming's left-hand rule. Imagine an electron enters a uniform magnetic field at right angles to the field lines. Let's say the magnetic field itself is pointing vertically downwards, and the electron is moving horizontally towards the right. The question is, what is the direction of the force acting on the electron?
Okay, electron moving right, field pointing down. What's the first step?
First, a crucial point you must recall when dealing with electrons or negative charges. The direction of conventional current is always taken to be opposite to the direction of motion of electrons.
Ah, right. Conventional current is opposite to electron flow. So if the electron moves right, the conventional current is effectively flowing.
Exactly. The effective direction of conventional current is towards the left. Now we have the directions we need for Fleming's left-hand rule. Field is downwards, current is leftwards.
Okay, now apply the rule. Left hand, forefinger, field points down, middle finger, current points left.
Okay, hold that position. Forefinger down, middle finger left. What direction is your thumb force pointing now?
My thumb. It's pointing straight forward, like away from me, into the page or screen.
Perfect. If you've done it correctly, your thumb will be pointing into the page or into the plane of whatever surface you're visualizing this on. Therefore, the force acting on the electron will be directed into the page. This type of problem, often involving electrons or protons entering magnetic fields, is very common in competitive entrance tests like J and NCERT. So practicing this application is absolutely key.
Got it. Need to remember the opposite direction for electron current, then apply the left-hand rule. That seems powerful. What uses this force principle?
This principle of force on current-carrying conductors and magnetic fields isn't just a theoretical concept or an exam trick. It's the fundamental operational basis for so many crucial devices in our modern world. The most prominent example is the electric motor.
Electric motors, right. They make things spin.
Exactly. An electric motor is designed specifically to convert electrical energy into mechanical energy rotational motion. It uses this very force on current-carrying coils placed within a magnetic field to generate torque and make a shaft rotate. This runs everything from tiny motors and toys and fans to washing machines, pumps, electric vehicles, and massive industrial machinery.
So Fleming's left-hand rule basically explains how motors work.
It's the core principle behind the force that creates the rotation, yes. It's also central to how electric generators work, though that involves the reverse effect, electromagnetic induction, often explained using Fleming's right-hand rule, which we'll cover later. This force is also used in devices like loudspeakers.
Loudspeakers, how?
In a loudspeaker, an electric current representing the audio signal passes through a coil attached to a cone, and this coil is placed in a magnetic field. The varying current causes a varying force. Fleming's left-hand rule again, making the coil and cone vibrate back and forth rapidly, which creates the sound waves we hear. Microphones often use the reverse principle, and it's also used in various sensitive measuring instruments like galvanometers. Understanding Fleming's left-hand rule literally unlocks the working principles of these indispensable devices.
Wow, okay. Motors, speakers. Are there any other, maybe less obvious applications? You mentioned MRI earlier. Does that use this force?
That's a great link back. Well, MRI, magnetic resonance imaging, primarily uses the magnetic properties of atomic nuclei, specifically hydrogen protons and water, and how they respond to strong magnetic fields and radio waves. The generation of those incredibly strong, uniform magnetic fields needed for MRI often relies on powerful electromagnets, typically superconducting solenoids. So the principles we discussed about solenoids creating strong fields are fundamental to MRI technology.
Okay, so the solenoid part is key.
Yes, and interestingly, magnetism plays a surprisingly vital role, even within our own bodies, which MRI helps to image. Even the incredibly weak electrical currents caused by ions moving along our nerve cells to transmit impulses, like when you decide to lift your finger or when you feel something touch your skin, produce their own tiny magnetic fields.
Our nerves make magnetic fields, seriously.
They do. They are incredibly weak, maybe about 1/10,000th, 10^9 of the Earth's natural magnetic field, so very hard to detect. However, two main organs in the human body produce collective electrical activity that generates magnetic fields significant enough to be detected externally with sensitive instruments. The heart, generating a magnetocardiogram or NCG, and the brain, generating a magnetoencephalogram or MEG.
So you can measure the magnetic field of the heart and brain?
Yes, but it requires very sophisticated detectors. The analysis of these intrinsic magnetic fields, which vary with organ activity, can provide diagnostic information. But the much more common clinical application involving magnetism is MRI. As I mentioned, MRI machines use extremely strong external magnetic fields, often generated by superconducting solenoids, combined with radio frequency pulses. These interact with the hydrogen nuclei in the body's water and fat molecules. By detecting the signals emitted by these nuclei as they relax back after the radio pulse, the machine can construct incredibly detailed cross-sectional images of organs, soft tissues, bone, and virtually any other internal body structure.
And it doesn't use X-rays, right?
Correct. A major advantage of MRI is that unlike X-rays or CT scans, it does not use ionizing radiation, making it generally safer for repeated examinations. The detailed analysis of these MRI images helps medical professionals make accurate diagnoses for a huge range of conditions, from torn ligaments and tumors to brain disorders and heart problems. It's a prime example of how a concept from physics electromagnetism directly helps in saving lives and improving healthcare daily.
That's amazing. From Oersted's compass to detailed body scans, physics really is everywhere.
It truly is. We've journeyed from tiny compass deflections to life-saving MRI machines, all stemming from the magnetic effects of electric current. But as this incredible force becomes such an integral part of our daily lives, literally flowing through the walls of our homes, understanding its safe handling becomes absolutely paramount.
Right. All this electricity at home needs to be safe.
Exactly. So let's bring our focus back home, quite literally, and explore the physics behind our domestic electric circuits. We need to understand the components, how they're connected, and especially the crucial safety mechanisms built in. This section is vital, not only for your fundamental understanding of how electricity reaches your home and powers your devices, but also because these safety aspects are very frequently tested in board exams and often appear as general awareness or general science questions in competitive exams like UPSC or SSC.
Okay, domestic circuits and safety. What's the basic setup?
In our homes across India, we receive our supply of electric power through what is called the main supply, or simply the mains. This power typically comes either through overhead electric poles carrying thick cables, which is common in many areas, or increasingly through underground cables, especially in newer developments or cities.
Okay, the power comes from outside via cables.
Right. The standard potential difference, or voltage, supplied between the two main wires that enter your home is typically 220 volts. This is the standard AC voltage in India, and it operates at a frequency of 50 hertz.
220 volts, 50 hertz. What does the 50 hertz mean again?
The 50 hertz frequency means the alternating current, AC, changes its direction of flow back and forth 50 times every second. It completes 50 full cycles per second. Now, the wires bringing this power into our homes have distinct insulation colors for easy identification and, crucially, for safety during installation and repair.
Yeah, I've seen different colored wires, red, black, green.
Exactly. By convention in India, the wire with red insulation is called the live wire. This is the wire that carries the high potential 220V relative to neutral earth and is the primary path for current entering your appliance. It's sometimes referred to as the positive or phase wire, though in AC, its polarity continuously reverses.
Red is live. That sounds important to remember.
Very. The other main wire, typically with black insulation, is called the neutral wire. This wire provides the return path for the current, completing the circuit back to the supply. It is ideally maintained at or near zero potential, earth potential. So the 220V potential difference exists between the live red and neutral black wires.
Okay, red live wire, black neutral wire, 220V between them. Where do they go first?
These live and neutral wires first enter your house, usually at the meter board. They pass through an electricity meter, which is the device owned by the power company that measures how much electrical energy, in kilowatt hours or units, your household consumes.
The meter that generates the bill.
That's the one. After the meter, the wires typically pass through a main fuse, which is a critical safety device we'll discuss in more detail shortly, and then connect to a main switch. This main switch allows you to completely cut off the power supply to the entire house if needed for safety during repairs or in emergencies.
Meter, main fuse, main switch. Got it. Then where?
From this main switch, the electricity is then distributed through wiring within the house to separate circuits. These circuits feed power to various rooms, lights, fans, and plug sockets. Often, for safety and load management, homes have two main types of circuits based on their current carrying capacity or rating.
Different circuits for different things.
Yes. One circuit is usually rated for a higher current, typically 15 amperes, 15A. This circuit is designed for appliances that draw a lot of power, things with heating elements or powerful motors, like electric geysers for hot water, large air coolers or air conditioners, electric ovens, or refrigerators. These need thicker wires and higher rated sockets.
15 amp circuit for heavy appliances. What's the other one?
The other circuit is typically rated for a lower current, usually 5 amperes, 5A. This circuit is used for lower power appliances like light bulbs, ceiling fans, televisions, phone chargers, and other small electronic devices. Using separate circuits prevents overloading a single circuit with too many high-power devices.
Okay, 15A for power-hungry stuff, 5A for lights and fans. That makes sense. Now, about that third wire you mentioned, the green one, you said it was important. I'd always noticed that in our 3-pin plugs, there's that third pin, usually thicker and longer, connected to the green wire. I've wondered what its specific purpose is, beyond just the live and neutral needed for the current. It seems to be a different kind of connection.
That's an excellent and very, very important question. You've spotted a crucial safety component. The third wire, which by convention in India usually has green insulation, though sometimes you might see it as bare copper in older wiring systems, is indeed the earth wire, or sometimes called the ground wire.
Earth wire? Does it actually connect to the earth?
Yes, it does, quite literally. This green wire inside your house's wiring system is connected to a thick metal plate, often copper, or sometimes a long metal pipe or rod, that is buried deep in the earth, usually somewhere outside near the house, often in moist ground to ensure good electrical contact. It provides a direct, low-resistance path to the ground itself.
Wow, okay. A wire going straight into the ground. Why? What's its purpose?
Its primary purpose is as a critical safety measure. It's particularly important for those appliances that have a metallic body or casing. Think of common examples we use every day: an electric iron, a toaster, a microwave oven, a table fan, a washing machine, or a refrigerator. The outer metallic casing or body of these appliances is internally connected directly to this earth wire via the earth pin on the plug.
So the metal body is connected to the ground through the green wire. How does that make it safer?
Let's understand its safety mechanism by considering what could go wrong. Imagine a scenario where, due to some internal fault in the appliance, perhaps damaged insulation on the live wire inside, or just wear and tear of the live wire, accidentally comes into direct contact with the metallic body of the appliance.
Okay, the live wire touches the metal case. That sounds bad.
It is potentially very dangerous. If there were no earth wire connected to that metal body, the entire metal casing would become live at 220 volts. Anyone touching that appliance would then provide a path for the current to flow through their body to the earth, since we're usually standing on the ground or touching something connected to it, resulting in a severe, potentially fatal electric shock.
Yikes.
However, with the earth wire properly connected to the metallic body, things are very different. If the live wire touches the body, the earth wire immediately provides a dedicated, very low-resistance conducting path for this fault current to flow directly and safely into the earth.
So the current goes through the green wire instead of through me.
Exactly. Because the earth wire offers a much easier path, lower resistance than your body, the vast majority of the fault current flows through it. This large current flow will also likely cause the fuse to blow or the circuit breaker to trip immediately, cutting off the power supply altogether. Crucially, because the body is connected to Earth, its potential remains at or very close to zero, the same potential as the Earth, even if the live wire is touching it internally. So, if someone touches the appliance in this faulty condition, there's little or no potential difference across their body, preventing them from getting a severe electric shock. This earthing system is a vital safety feature, especially for metal-cased appliances, and understanding its function is critical for both practical safety and for exam questions focusing on domestic circuits.
Okay, the earth wire is literally a lifesaver then, providing a safe path for fault currents. That's very clear. How are appliances connected inside the house? You mentioned circuits. Are they in series or parallel?
Good question about the connection. In our domestic circuits, different appliances, lights, fans, sockets are always connected in parallel across the live, red, and neutral black wires within each circuit, like the 5A or 15A circuit.
Always in parallel. Why parallel?
Connecting them in parallel is crucial for a few key reasons. Firstly, it ensures that each individual appliance receives the full 220V potential difference from the supply. This voltage is necessary for them to operate correctly at their designed power rating and efficiency. If they were in series, the voltage would get divided among them and none might work properly.
Ah, right. Voltage divides in series. Okay, so parallel gives full voltage to everything. What else?
Secondly, and equally important for convenience, parallel connection allows each appliance to operate independently of the others. You can switch on your light bulb without having to turn on the fan, and vice versa. If appliances were connected in series, like old-fashioned fairy lights, turning one off, or if one bulb failed, would break the entire circuit, and all the other appliances in that series string would stop working. Parallel connection avoids this problem entirely.
Okay, parallel for independent operation and full voltage. Makes sense. Now, you mentioned the main fuse earlier, and also the earth wire helping to blow a fuse. What exactly is the role of the fuse?
The electric fuse is perhaps the single most important safety device in all domestic circuits. You'll find a main fuse for the whole house, and often individual fuses, or more commonly now miniature circuit breakers or MCBs, which serve the same purpose but are resettable, protecting separate circuits or even built into some appliance plugs. We actually touched upon its working principle in our previous deep dive on electricity when we discussed the heating effects of current, Joule heating, but it's absolutely worth reiterating its critical role here in the context of safety.
Right, Joule heating, H equals ISIC7TRT.
Heat depends on current squared.
Exactly.
Yeah.
A fuse is designed specifically to protect expensive appliances, the household wiring itself, and ultimately prevent fires by automatically interrupting the circuit when the current becomes dangerously high. This dangerously high current usually arises from two main situations: overloading and short-circuiting. Overloading and short-circuiting, what's the difference?
Let's define them. Short-circuiting is probably the more abrupt and dangerous one. This occurs when the live wire, red, and the neutral wire, black, accidentally come into direct contact with each other, with very little resistance between them.
How would they touch directly?
It can happen if the insulation on the wires gets damaged or wears out over time, maybe due to friction, heat, or rodents chewing on them. Or it could happen due to an internal fault within an appliance itself, where wires cross or components fail, causing the live and neutral paths to connect directly.
Okay, live touches neutral. What happens then?
In such a situation, the total resistance of the circuit becomes extremely low, practically close to zero, just the resistance of the wires themselves. Now think about Ohm's law. Current, I, voltage V, resistance R. If the voltage is 220V and the resistance R suddenly drops to near zero, what happens to the current I?
V divided by almost zero. The current becomes huge, infinitely large.
Theoretically, yes. Practically, it becomes very, very large, hundreds or even thousands of amperes for a fraction of a second, limited only by the capacity of the power source and the tiny resistance of the wires. This extremely large, sudden surge in current is what we call a short circuit.
Okay, that sounds really bad for the wiring in appliances.
Extremely bad. It can cause intense heating, melt wires, damage appliances instantly, and potentially start fires. Now, what about overloading?
Overloading, is that less sudden?
Yes, overloading is usually a more gradual but still dangerous increase in current above the safe limit for that particular circuit. It can sometimes occur due to an accidental, temporary hike in the supply voltage coming from the main grid, though this is less common and usually handled by other protective devices. More frequently, overloading is simply caused by us connecting too many appliances to a single socket or a single circuit, especially if they're high-power appliances.
Like plugging a geyser, a heater, and an electric kettle all into the same 5A socket using an extension cord.
Exactly. That's a classic recipe for overloading. Every socket, every wire, and every circuit is designed to safely carry only a certain maximum current, like 5A or 15A. When you connect too many devices, the total current drawn by all of them added together exceeds this safe limit. The wires start to carry more current than they are designed for, which leads to overheating, potentially melting the insulation and causing a fire hazard over time, even without a sudden short circuit.
Okay, so short circuit is a sudden, massive current surge. Overloading is drawing too much current continuously. How does the fuse stop either of these?
Here's where the simple genius of the fuse comes in. When either overloading or a short circuit occurs, the excessively high current starts flowing through the fuse wire. Now, remember Joule heating, HUA, ITO, and RT. The heat generated in a wire is proportional to the square of the current. So even a moderate overload current, and definitely a massive short circuit current, causes the fuse wire to heat up extremely rapidly.
It gets hot very quickly because the current I is high.
Precisely. And the key design feature of a fuse wire is that it's made of a special alloy, often a tin lead alloy or similar, that has two crucial properties: adequate conductivity to carry the normal current, but a very low melting point.
Low melting point, so it melts easily.
Exactly. When the excessive current caused by the overload or short circuit flows, the fuse wire heats up so quickly that it reaches its melting point almost instantly and melts or blows. This melting physically breaks the circuit, creating an air gap that the current cannot cross.
So it acts like an automatic switch that breaks when the current is too high.
That's a perfect way to put it. It sacrifices itself to protect the rest of the circuit. This immediate interruption of the current flow prevents serious damage to all the connected appliances, which might be much more expensive than the fuse. And, most importantly, avoids the risk of electrical fires caused by overheated wiring or short circuits. That's why replacing a blown fuse with a wire of the wrong rating, or worse, bypassing it altogether, is incredibly dangerous.
Right. Always replace a fuse with one of the correct rating. So, to avoid overloading in the first place, what should we do?
Good practical question. To avoid overloading, the main thing is to be mindful of the power ratings of your appliances and the capacity of your circuits and sockets. Don't plug too many high-power appliances, like heaters, irons, kettles, microwaves, into a single socket, especially if it's only a 5A circuit. Use the 15A sockets for those heavy-duty items. Also, make it a habit to periodically check the condition of plugs, sockets, and appliance cords for any signs of damage, fraying, or overheating, and get them repaired or replaced promptly by a qualified electrician. Basic electrical safety awareness goes a long way.
Okay, that's very clear. Fuses and earthing are vital safety nets.
Absolutely vital. Understanding them isn't just for exams, it's for everyday safety in our homes. Right, that covers quite a lot of ground. Shall we try and quickly summarize the key points from our deep dive today?
Yes, please. A quick recap would be really helpful to consolidate everything.
Okay, so to quickly recap our comprehensive deep dive today, we started right at the beginning with Oersted's groundbreaking, almost accidental discovery back in 1820. That was the key moment that first revealed the intrinsic link between electricity and magnetism, showing how an electric current creates a magnetic field around it. Remember the compass needle deflection?
Yep, Oersted and the compass. Got it.
Then we spent some time exploring magnetic fields themselves, focusing on the fields around permanent bar magnets. We learned how to visualize these fields using magnetic field lines, and, crucially, we went over their key properties. They are vector quantities. They form closed loops, north to south outside, south to north inside. Their density indicates the field strength, and, importantly, they never intersect each other.
The 5 properties of field lines. Okay.
Next, we shifted focus to the magnetic fields produced by currents. We looked at the pattern around a long, straight wire, remember the concentric circles, and we learned the indispensable right-hand thumb rule to determine the direction of these fields. Thumb for current, fingers curl in the field direction.
Right-hand thumb rule for straight wires. Concentric circles.
Then we extended that to current in a circular loop, finding the field concentrates at the center, and then to a solenoid, that long coil, which acts very much like a bar magnet, and, crucially, produces a strong, uniform magnetic field inside it. This led us to the idea of electromagnets.
Solenoids and electromagnets, uniform field inside. Check.
Following that, we flipped the perspective and understood the equally vital concept of the force experienced by a current-carrying conductor when it's placed in an external magnetic field. We acknowledged Ampere's contribution here. We saw this force in action with the swinging aluminum rod experiment, and we learned how to predict the direction of this force using Fleming's left-hand rule.
Fleming's left-hand rule, father, mother, child. Force, field, current, essential for motors.
Absolutely essential for understanding electric motors, which rely on this principle. We also briefly touched upon the fascinating and life-saving application of magnetism and related physics in medicine, specifically with magnetic resonance imaging, or MRI, which uses strong magnetic fields to see inside the body.
MRI has a high-tech application.
Right. And finally, we brought it all home, analyzing the critical components and safety measures within our domestic electric circuits. We distinguish between the live, red, neutral black, and the absolutely essential earth, green wires. And we thoroughly understood the life-saving role of electric fuses and circuit breakers in protecting our homes and appliances against the dangers of overloading and short-circuiting by interrupting excessive current flow.
Live, neutral, earth, fuse, overloading, short-circuiting, domestic safety. Got it. That's a great summary.
Excellent. Now, to really lock this knowledge in and make sure you can apply it effectively for your board exams and competitive entrance tests, here are a few actionable tips.
Okay, exam tips are always welcome.
First, I strongly recommend you thoroughly revise all the magnetic field diagrams, bar magnet, straight wire, loop, solenoid, and the associated rules directly from your NCERT textbook or equivalent state board book. Pay special attention to the diagrams and the examples and the in-text questions. Practice actually drawing these field patterns repeatedly until they become second nature. Visualizing them correctly is half the battle.
Practice drawing the field lines, okay?
Second, make absolutely sure you can apply both the right-hand thumb rule for finding field direction from current and Fleming's left-hand rule for finding force direction from field and current confidently and accurately to different scenarios. Don't just memorize them. Understand how to orient your hands, maybe challenge yourself. Draw out a few simple problems. Current going left, field going up, what's the force? Electron going down, field going into the page, what's the force? Solve them using your hand rules. This active practice is invaluable for speed and accuracy in exams.
Right. Active practice with the hand rules is key.
Third, really understand the safety aspects of domestic circuits. Be crystal clear on the specific function of the earth wire, why it's connected to the metal body, and how it prevents shocks. And understand precisely how an electric fuse works the role of joule heating and the low melting point in protecting against overloading and short-circuiting. These are very common practical application questions in theory papers, viva voce, and also in the general science or general awareness sections of various competitive exams.
Earth wire and fuse function for safety questions. Got it.
Yeah, and finally, try to actively connect these fundamental concepts to the working principles of larger devices, especially the electric motor, and, looking ahead, the electric generator. Understanding the underlying physics of how these machines operate is often a requirement for higher-level competitive exams like JEE or NEET, where application-based questions are common.
Connect the basics to motors and generators. Okay, great tips.
Good. Keep these in mind as you revise. Now, just a final thought to leave you with. Think about this for a moment. That simple, unexpected deflection of a tiny compass needle, accidentally observed by Hans Christian Oersted over 2 centuries ago in a lecture hall. It seemed so minor at the time, perhaps just a curious anomaly. Yet that single observation, pursued with scientific curiosity and rigor, blossomed into the vast and intricate field of electromagnetism. It led down the line to practically everything electrical and electronic in our modern world, from the giant industrial electromagnets we discussed, capable of lifting tons of scrap metal, to the incredibly precise medical imaging devices like MRI machines that can peer deep inside the human body, diagnosing diseases and saving lives without needing a single surgical cut.
It's amazing how one small discovery can lead to so much.
It truly is. It's a powerful reminder, I think, that sometimes in science, the smallest observation, the thing that seems slightly off or unexpected, can hold the key to unlocking the biggest scientific breakthroughs and completely reshaping our understanding of the universe and our technological capabilities. So the message is, Keep exploring, keep questioning, keep noticing the small things, and always keep that scientific curiosity alive.